Hi everyone, I'm Shajesh and this is my final presentation for the compiler design and implementation course. I'll be going over the compiler design philosophy, the implementation details with regards to my symbol table and some error handling. I'll show a sample of my programs, one to compute Fibonacci numbers and the other one to compute the factors of a given number. I'll touch on the optimizations pursued and provide a demo with the optimization on the compute factors program to show what the speed up was in terms of the wall clock time. And then I have some final words and that should be it. All right. For this course, I decided perhaps predict to roll my own compiler from scratch, sort of understand the interfaces between the stages and plan out the structures better. I would say that that was an educational, if not difficult undertaking. As with the philosophy of the compiler in this course, I've implemented it in modular stages with the scanner, parser, symbol table generation, type checking, IR generation, and optimization plus MIPS generation. All of these are modular with some dependencies, but strictly in the forward direction. All right, so this slide presents some implementation details regarding my symbol table. For the symbol table implementation, which is shared by the string as well as the label tables, I implemented a hash table in order to deal with collisions in the hash value. Because my hash table is of a fixed length, I added buckets to each index, which is that if two values map to the same hash index, I just use the linked list to store all of them at the index as a chain of linked nodes. This approach helped me with a quick lookup of the symbol table for error detection. Like the overhead for searching my symbol table for multiple definitions or declarations was not so much because of the choice of this implementation. Another implementation detail I wanted to highlight was the error handling. In order to fully utilize this compiler for some work that is productive, I also wanted to indicate if something went wrong, what went wrong, and where. So with each error, I also print out a unique code for each type of error, the line and column numbers for tracing the error back to the source, and a descriptive message. So this is a small example that's representative of what would happen in this program, which is very short. I'm trying to access B, which is previously undeclared, and that yields a error message of saying that in the usage of variable B in line number 4, column 7, the error was this code, and that it was a undeclared identifier, which is not allowed. I'd now like to go and show you an example of a program that I wrote and compiled with the compiler. It's a Fibonacci program. It's very simple. It takes in an integer count of how many numbers to print, and then in a loop it prints all the Fibonacci numbers up to that count. One detail to note is that the upper limit for the number of Fibonacci numbers to print is unbounded, but beyond a certain index, there will be an integer overflow because of the addition operation, and the results will effectively be the wraparound values of those numbers. So might not be so useful beyond a certain point, but it highlights the following features of our language, which is function calls, the Fibonacci's function call from main, syscalls for reading integers, printing integers, and printing strings, addition, and then loop constructs like the while loop and the simple if else branching. I'll go over to the console and show you the Fibonacci program now. Here's a demo of the Fibonacci program. The program itself is on this right pane. It asks you how many Fibonacci numbers you want to print, minimum 2. And then let's say I want to print 10 numbers. Just hit enter and it'll print the first 10 Fibonacci numbers. It's quite a simple program, and it gave me quite a kick when I got it working for the first time. The second program I'd like to highlight is a program to compute the factors, integer factors of a number. It will take an integer value from the user and then print to the console all of those numbers that exactly divide this number with the remainder of 0. I thought this was slightly different from the previous one because it gave me an opportunity to use the division plus the mf high functionality to calculate the remainder. And also similar to the previous program, it also highlights some syscalls, the loop construct, and some simple if else branching. So I'll go back to the console and show you the program to compute the factors. Here's the program to compute the factors of a given number, and let's run it. So let's say I want to compute all of the factors of number 32768. I enter the number, and then it prints to the console all of the factors that it identified for this number. It's quite simple. You can try it with a slightly bigger number also, and it's pretty much going to print all of the factors to console. Some of the optimizations I pursued were firstly the T register spill detection, which is enabled for the O1 and O2 levels. The register allocation in my compiler is quite simple. It defaults to using the S registers and spills to the T registers upon exhaustion of the S registers. Each function keeps track of the T registers it used and marks them as requiring to be saved when a function call is encountered. So when we encounter a function call and we need to switch contexts, only those registers that were used are stored to the stack. This is quite useful because it avoids having to default to storing all 10 T registers and makes the code somewhat better. The second optimization I pursued was optimization for comparison plus branching. This involves optimization of a code that looks something like if A equals B or if A not equal B, and similar comparisons immediately followed by a branching with an if. Without optimization, this is the code that I use to generate, which is to XOR the two numbers and then use the SLTU instruction to compare it. And if it was equal to 0, then I would jump to a generated label, else I would continue with the program flow. The set of 3 instructions can be compacted into a single instruction, BNE, which takes in the 2 numbers to compare if they're equal or not. And if they're not equal, to jump to this generated label, else continue with the program execution. So next I'd like to demo like the results of my compute factors program with the optimizations. I have them compiled with O0, O1, and O2. And when I ran them with SPIM, I found that like the improvement from O0 to O1 was pretty drastic by itself, with just the improvements to the T register handling. And then from O1 to O2, there was a further improvement due to the additional optimization of the compare plus branch instructions. So I'll go back to the console to show you the demo of the 3 O factors and their improvements. Let's first run the program with the O0. I'm giving it an input of 65536, and we can see that it executed in about 2.7 seconds. Now, if I switch to the version that was compiled with the O2 compiler flag, we can see that it takes a little bit lower, which is 2.5 seconds. With different profiling instances, like I have varied results, but on average, I do find an improvement between the unoptimized version and the optimized versions. Finally, I'd like to sort of take a step back and take a look at the course as a whole, having gone past it in what seems like no time at all. Around 11,000 lines of code later, I still feel like there's a lot that's left to be done, and I certainly do feel like I'll continue to work on this project even after this course is over. Building a compiler from scratch was really unparalleled educationally, and it sort of changed my assumptions of what I thought was possible. And the fact that if I encounter a problem that would require parts of or a completely new compiler as well, I would now be less intimidated about that problem than I was before. Of course, it wasn't very easy, going through several existential crises and questioning your abilities while also experiencing the thrills of seeing something work was truly a roller coaster. But I'm really glad I took this course, and I'm grateful for the opportunity. And I hope to see all of you in another class in the future. Um, I'm gonna leave with a small meme of how I feel about deciding to roll my own compiler and ignoring the compiler framework. I think it can be fully summarized by uh, this graphic here. Thank you so much. Bye.